see, can you go down to the pad here? I guess I'm right here. Yeah, great. Okay. To remind you where we are, we're looking at second-order systems. In fact, specifically, we're looking at the differential equation ay prime prime plus by prime plus cy equals 0. And we're just studying the different types of solutions you can get. Last time we saw that after you take the Laplace transform, the following polynomial comes up, quadratic in fact, that this polynomial comes up, whoops. And the question then is the actual nature of the inverse Laplace transform, which gives you the solution y, depends on the roots of this polynomial. And we divided this into 3 cases. One case was when both roots are real. The second case is when they're real and equal, which is what we looked at just last time. And then the third case is where the roots are actually complex. And that's going to be, in fact, probably arguably the most interesting case. So to finish up this part on real equal roots, this happens when b squared is 4ac. So that term squared, b squared minus 4ac is 0. You get the same roots. And in this case, the Laplace transform has this form, which we write in this form here. And when all the smoke clears, the Laplace transform, the solution y has the following form. Its y of t is r1 e to the lambda t plus r2 t e to the lambda t. And if you like, you can write that as r1 plus r2 t times e to the lambda t. So that's the solution. Now, there's a very interesting point here, and that is that the formula for the solution is now different. You now have a t e to the lambda t term. If lambda is negative, that's a function that looks something like that. It grows for a while. It reaches its peak at 1 over lambda. And then above that, even though the term t is increasing, the term e to the lambda t is decreasing faster, and so it gets killed off by that. So that's what that looks like. It's very different from an exponential. Okay, when this occurs, the system is often called critically damped if lambda is less than 0. And that's an idea that plays an important role in a bunch of things, but often in mechanics. So let's look at an example. It's a mass spring damper. And this can mean a lot. This can, of course, it can be a very simple model of a lot of things. First of all, this could be a vehicle, the simplest model of a vehicle suspension. So that's the vehicle. This is the road surface here. That's the stiffness of the suspension. It probably includes some stiffness from the suspension and the tires. And B is a damping. And that also comes from both tires and shock absorbers, this type of thing. Here, before, we actually had the road. We were actually going to take into account the fact that the road height was changing. And we're not going to do that now. It's just a vehicle running on level ground. And what we're going to do is we're going to look at the natural response. What the natural response is it tells you what happens to the vehicle when it's in some initial condition, or if you push down on it and then let go, see what happens, that kind of thing. That's the natural response. Okay? Okay, so if we work this out with mass, stiffness both 1 and damping 2, that gives you the differential equation s squared. Well, it gives you y double prime plus 2y prime plus y. The characteristic polynomial is s squared plus 2s plus 1, which, sure enough, has real and equal roots. Both roots are minus 1. Okay? So the roots of the characteristic polynomial are both minus 1, and so the solution has this form. Now we'll try, what we're going to do is we're going to work out the solution for the following initial condition. That is that it's initially at 0, but it has an initial velocity. So for example, it's moving upward. That's what y prime equals 1 is. And we'll see intuitively you know what the solution is. If this thing is originally at 0 height, meaning the spring is putting no force on you and you're moving upward, well, it's not going to immediately stop. It will move upward. The minute it moves upward, the spring will pull you back. But in fact, as long as you're moving, the damping will also be putting a restoring force on you. Okay? Well, if you go through if you just simply solve the equations, you get R1 is 0 and R2 is 1. And so you get your classic response right here, which is the TE to the minus T response. And so if we plot that, it looks something like this. So again, physically, well, you should check that if you take this function, compute its first and second derivative, and plug it in. Hey, I see a typo. There's a 2 missing there. Boy, who makes up these lecture notes anyway? Huh. Yeah. And where were the TAs who were supposed to check? I don't know. I don't know what's happening around here. Okay. No, it's my fault. So you should, if you take this, take its first and second derivative and add up the second derivative plus twice the derivative to itself, you better get 0 identically. Okay? And it will happen. Here's the solution. It looks like this. And first of all, it looks like what I drew. This is your basic TE to the minus T response. And in fact, intuitively, it makes perfect sense. This shows you the motion of, for example, a car. Actually, now it can just be parked. When it's sitting there at its equilibrium height, and for some reason, which we don't specify, it has an initial velocity upwards. That's the idea. And so what happens is it goes up until up here the spring force and the damping force are enough to actually pull it down and pull it down, and it goes down like that. And this shows you the rough picture of how this works. Okay. Later we'll see, in fact, that this is a fairly special type of response, but it's called critical damping. That's what it's called. Okay? And a lot of systems used to be. I guess back in the days when you didn't have computers and couldn't actually figure things out that carefully, critical damping was actually widely used. It's just kind of not a bad design for a large number of second-order systems. And in fact, it was sort of like a target. That's not true anymore when it's easy enough to just sort of make these plots and work things out yourself. But this was a target, let's say in 1920s, 1930s, and 40s. When you were designing systems, critical damping was quite common as the target specification. Okay. Now we get to the last and probably the most interesting case for second-order differential equation. Because now you're going to see something that you haven't seen before from 101. Hopefully you've seen it in some other class, like a math class, for example. And that is, we're going to look at the solution of this second-order differential equation when b squared minus 4ac is negative. So when you take the square root of b squared minus 4ac, you're going to get complex numbers. So the roots are now complex. Now, in this case, the roots are given by two complex numbers which are conjugates of each other. In other words, on the complex plane, if that's one root, the other root is over here. Conjugate means you flip the sign of the imaginary part, and that means you reflect it through the real axis. So if that's a root, that's the other one. They have the form sigma plus j omega and sigma minus j omega. Sigma is sort of the real part, and omega is the imaginary part. Okay? So this is the idea. These symbols, sigma and omega and indeed lambda, these are all kind of traditional symbols. I'm using them. I could use anything I like. I could use alpha and beta, W and Z. These are the traditional symbols recognized in at least several fields that I know of would use sigma and omega to traditionally denote real and imaginary parts of roots of the characteristic polynomial. Okay, so there's lots of ways to work out what these are. For example, sigma is minus b over 2a, and omega is basically b squared minus 4ac square root with the 2a in the bottom. You can write that this way if you like. Okay? You can also write it out this way, that as squared plus bs plus c is a times s minus lambda times s minus lambda bar, where that's the conjugate. So that's the other way. And if you multiply this out, you get various interesting relations. For example, a times lambda plus lambda bar, which is the s, if you have a minus there, that's the s coefficient here, that has to equal b. And so this of course is twice the real part of lambda, and so we'd recover this one. So anyway, it's important to actually be pretty facile with the going back and forth between, say, A, B, and C here, and the relations with the two roots, the real and the imaginary part. Okay. Well, the Laplace transform of y, the funny part is that hasn't changed. In other words, the Laplace transform of y is this, and it's this if the roots are real and distinct. It's this if the roots are real and equal, and it's this if the roots are imaginary, complex. It's always the same. The difference is that when we take the inverse Laplace transform, we get a very different type of formula in the three different cases. So here, we're going to write this as r over s minus lambda plus r bar over s minus lambda bar. And since lambda and r are now complex numbers, you could object quite reasonably. The reason you could object is why, when we started off this adventure here with this differential equation, I didn't say it, but implicitly, y is real. Y is real. Now, it's the motion of an automobile on a suspension, its displacement is measured in centimeters. Okay? It's not complex. So here, I've split up something into two pieces which are complex. Okay? Well, this is not unlike what happened in 101 when you look at the dynamics of a circuit with inductors or capacitors in sinusoidal steady state, and the next thing you know, all sorts of things are complex, and so on. So it's one of those things where in the end we're going to get the solution, and in fact it's nobody's business how we got to the solution as long as in the end the solution is right. Okay? So in other words, that's the idea. So I'm going to write it this way. You can work out what r and r bar are. That's actually the topic of our next lecture. And so there are many expressions to get r and r bar here, or the conjugate. And one is this. Here's one in terms of various things, in terms of alpha, beta, A, B, and C. Here's one expression. There's lots of others. Right now, actually, what we're doing is we're actually most interested now in the form of the solution, not the exact solution, although this gives the exact solution. Okay. So the inverse Laplace transform of this is a sum of these two terms. Now, I've asked you to accept the fact that these are complex. The nice part is when you add them together, all the imaginary stuff goes away, and you're back to something real, right? So it's like representing cosine as e to the j omega t minus e to the minus j omega t, and then maybe divided by 2, right? You write a sinusoid as a sum of two exponential terms, and it just makes some calculations easier. So here, there's many ways to write y, but one is this. You can write it as twice the real part of r e to the lambda t. That's a very simple way to write it. You can write it this way. E to the sigma t times a number u cosine omega t plus v sine omega t. Or you can express this is a sinusoid in, I guess, cosine sine form, or some people call this in quadrature form. Quadrature meaning that these two sinusoids are 90 degrees out of phase. Or, actually, some people call this the IQ representation. That's another term used. You don't need to know this. I'm just mentioning this. IQ means the in phase and the quadrature component. So these are, depending on the field, for example, in communications, universally people refer to these as the IQ. U is the I component and V is the Q component. Or you can write it in the form probably that you used most in 101, which is cosine omega t plus phi. And phi is referred to as the phase angle. Okay, so these are the different ways. And I guess from 101, you certainly know how to go back and forth between this representation. Well, actually, all three. You should be able to go back between all three. Go back and forth between all three. So that's just 101 stuff. The only new thing here is you did this kind of stuff in 101, except that this term r wasn't there. The real part wasn't there. So this term wasn't there. Now, let's just look at it and see what it says. What it says is it is a sinusoid here with a magnitude and a phase shift, but multiplied by an exponential. It's multiplied by an exponential, which is either growing or shrinking, depending on what sigma is. So here, there's lots of names for these things, but r is called the complex amplitude. Lambda is called the complex frequency. U and V are called the cosine sine or IQ components. and m and phi are called the amplitude and phase. Okay? Now, a lot of interesting things. This tells you a lot about how this works. First of all, if that term sigma, which is the real part of the roots, that's the real part of the roots of that characteristic polynomial. If it's positive, then what we have here is we have an exponentially growing sinusoid. Okay? If sigma is negative, we have an exponentially decaying sinusoid. If sigma is 0, in other words, if the real part of the roots of that polynomial are 0, you have a pure sinusoid. Okay? Another way to say the same thing is to say that the real part of this root of that characteristic polynomial, that gives you the exponential rate of decay or growth. So if sigma is plus 3, that tells you that there's an e to the 3t term in there, and it tells you that, for example, in 1 second, the solution got a lot bigger, specifically e cubed bigger, right? If sigma is minus 0.01, how long does it take for the exponential term to decay to, for example, 37%? What is it? If sigma is minus 0.01, what's it mean about the solution? How long does it take? 100 seconds, exactly. And if sigma is plus 0.01, what has happened in 100 seconds? It's grown by a factor of e, right? So it's a sinusoid, and it has grown by a factor of e, exactly. Okay? Now the other important thing, the other very important thing here is to point out what parts determine what. The nature of the solution, that is to say, whether it's a sum of two real exponentials, or whether it's got this t e to the lambda t, or whether it's a damped or growing or decaying exponentially growing or decaying sinusoid, this depends only on the characteristic polynomial, right? Those are the coefficients directly from the differential equation. Other things like the amplitude, the phase, the coefficients, how much of e to the lambda t is thrown in there and how much of t e to the lambda t is thrown in there in the critically damped case, these depend on the initial conditions. Okay? So that's an important thing to point out here. Okay. So if you ignore the sinusoid, this thing in front, that's called the envelope of y. And the picture is very simple. If the frequency is high and you plot this thing, it looks like this. This is plotted for the case where it's decaying. If it were growing, this thing would grow like that. Okay? And this is the case where the exponential growth term, or decay rate here, is kind of small compared to the sinusoid. So what you see here is, you get lots of cycles in there before you've either grown or decayed. Then it really does look like the envelope, because it's the envelope of the signals where you you draw a little dotted line connecting sort of the magnitude of it. Okay? So this is, it's called the envelope. And as we've already said, it's the real part of that differential equation. So since that real part is precisely minus b over 2a, now you will be able to look at a second-order differential equation and say things to look at it, and doing a quick calculation in your head, you'll be able to say whether or not the solutions are exponentially growing or decaying. Okay? Easily now. So for example, if a and b are both positive, what is sigma? What sign is sigma? It's negative. And what does that mean? Is that growth or decay? It's decay. So from now on, basically forever, when you see a second-order differential equation and you see a and b and c positive, here's what you're going to know is it's decaying. Okay? So these are the types of things you'll be able to say. And you'll know why. If you see s squared minus 5s plus 3, you know right off the bat we don't have a decaying solution. Okay? So we'll get back to that. Okay. So here's a good exercise, is to take this plot where I have axes for y and t. That's the solution of a second-order differential equation. And I could easily ask, what are sigma and omega here? Easily. In fact, let me show you what an outstanding quiz problem would be, except now that I tip you off, we can't use it, of course. We could, actually. I could say this is the solution of the following equation. Y double prime plus fy prime plus gy equals 0. I just arbitrarily took a equals 1. Or if you like, go back to the traditional symbols b and c. And I could say, that's the solution. I could ask you I could ask you all sorts of wonderful things. We could say, what are b and c? Totally reasonable question. There's the solution. What's b and c? This is inverse of solving a differential equation. Here's the solution. You tell me the differential equation. Totally reasonable question. So, okay. Now I've warned you. Actually, we should talk a little bit about how did you do it? What would you do first here? What do you have to do first? What do you need to identify? What parameters of this signal do you need to identify? Omega, and then the growth rate, sigma, right? How would you get omega from this? Could you? Yeah? What would you do? Just a rough. How would you calculate omega? Yeah, count some peaks or count a number of cycles and say you get 10 cycles in so many seconds. This tells you the period. And then, you'd do the right thing with 2 pi. You'd have to think a little bit before you got that right. But eventually, you'd find omega. Not eventually. I mean, it's not that hard. You either have to divide by 2 pi or multiply by 2 pi. I forget which. But you'd get omega, right? Well, you can always figure out what it is, right? Because you just write down cosine omega t and see if it fits see if it goes through as many bumps as you counted. So you get omega. And how would you get sigma here? How would you do it? Starts out with an amplitude of 1. This is like a 101 problem, except you just completely ignore the sinusoid stuff here. What do you do now? Yeah. You pick some point. In fact, to make it easy on yourself, if that's 1, you find 0.37 here, for example, and you go across. And if doing that gives you some reasonable estimate, then you say, oh, there's the time constant. I don't know what it is. Here, let's go across there. 2. Let's say it's 2. And so then you get sigma. Sigma is what if the time constant is 2? It's 1/2. Like sigma is a frequency. Okay? All right. So there's a couple of other interesting things to point out here is things involving the ratio of sigma to omega. That's unitless, right? Because this is a ratio of 2 frequencies. And what it tells you is if sigma is less than 0, it's the number of cycles to decay to 1%, and it's equal to 0.73 omega over sigma. That's, I guess informally, that's 0.7 omega over sigma. And omega over sigma, if you actually look at where that root is as a complex number, it's the ratio of, that's sigma, and that's omega. So although you'll get more and more used to this, the following is the case. When you see a root, and it's very near the imaginary axis, what it says is that the solution looks like this. This is called underdamped, by the way. Or in fact, in this case, qualitatively, someone would say this is lightly damped, is the way this would be described, as lightly damped. For example, if this were the response of an automobile suspension, what do you think? The question is, how would you like to be in there?
Have fun.
Yeah, it would be fun. Yeah, maybe once. Yeah, okay, so it wouldn't be that much fun. Okay. Now, on the other hand, later we're going to find we'll actually find some good things about this. Okay. So, if this were the response of a vehicle suspension, or say a building in an earthquake, this would definitely not be fun. Okay. So later we'll find out actually what the use of this is. We'll see. I'll give you a hint. If you didn't have systems with responses like this, you wouldn't have any wireless communication. So, okay, we'll get to that later. Okay, so here's a special case. It's the harmonic oscillator. The harmonic oscillator is when you have that term in the middle, that y prime term is 0. Then the real part of the roots are pure imaginary. They are plus minus j omega. That's the traditional way to write down the solution of the harmonic oscillator. And here the solutions are pure sinusoids. Okay, so if you hadn't already done so, it's probably a good idea to take that equation. You're going to encounter this everywhere. You're going to encounter it in quantum mechanics everywhere you go. You will not be able, mechanics, everything. You can't avoid that equation. This is It's the equation of the it's a harmonic oscillator. It's a second order equation with no y prime term. Now you know what that means. It means that the characteristic polynomial has roots which are pure imaginary. They don't have any real part at all, and so they're neither decaying nor growing. There was a question.
Yeah, does that correspond to the no dash pot in the...
Precisely.
Okay.
Yeah, this is what happens in the suspension when you remove the dash pot. Except you'd have to have there's damping and other things. Like a real spring always has a little bit of damping. But the fact is, you get things that are pretty close to this. For example, in mechanical structures in outer space. Very close. Very, very. You have things where they don't oscillate forever, of course, because they're small damping. But you can get things that will actually oscillate for a long, long time. Not so much on Earth, but okay. All right. So the solutions are purely sinusoidal, and here's some physical examples. They are very, very good to know because it's good to connect all of this. I feel very sorry for people who only think in terms of differential equations, because it just, I don't know, it's just a very boring world or something like, I don't know, if that's, but that's okay. So you have to figure the physical pictures here. So here are some. LC circuit. So just connect an inductor to a capacitor, work out the equations, and it's V prime prime plus 1 over LC V equals 0. Okay? So the oscillation frequency is 1 over square root LC. And it's a good thing to work out, to actually work out the units, right? I mean, is it true that is it true that 1 over the square root of Henry's times farads is in fact is 1 inverse seconds? And in fact, of course, it is. And so it says that if you have an inductor and a capacitor and you hook them together, then in fact the solution of that circuit is it'll oscillate. It'll just oscillate forever. Okay? And in fact that's what happens. It has to be a superconducting inductor here. Otherwise there's going to be some resistance and it won't oscillate forever. If there's a small resistance, what's going to happen is there's going to be a small y prime term there. And that's going to reflect itself in a small negative real part in the roots, and that's going to correspond then to something that looks sinusoidal, but is in fact decaying very slowly. We'll get to all of that in a minute. Okay, another one is a mass spring system. So an ideal mass stuck on top of an ideal spring with no losses of any kind anywhere, right? No losses. Will in fact oscillate. This is sort of like an ideal pendulum or something like that. If you take this, I guess you have to do this in outer space or whatever. So you take your mass and you scrunch it down and you let go. It will simply oscillate, and it will oscillate forever if this model is accurate, right? Which, of course, if you did this with a real spring, it would not be. But as a first cut, that's not a bad picture of what happens. And here, the oscillation frequency is square root k over m. And again, you have to check. Is it true that the square root of a mechanical stiffness divided by mass is a frequency? And it is. But these are your pictures of harmonic oscillators, or another way to say it is oscillatory systems with no damping, no mechanism for damping. And one other thing, just for fun, just to see how, if you're on your toes here. Suppose I say that I want to study this equation with a minus sign there. What happens now? Is the solution oscillatory? What happens now? This is it. This is the test to see if you're following what's going on. If you have, come on, I could argue this way. That's a second order differential equation, right? It looks I don't know, someone says, oh, that's an oscillator. And you go, all right, well, I just want to consider another one like that. It's not that much different. In fact, the only difference is that this coefficient over here is negative or what. So what do the solutions of that look like? Just qualitatively, what do they look like? Are they oscillatory? What are they? Huh? Well, it all comes down to the characteristic polynomial. What's the characteristic polynomial of this? It's s squared minus omega squared. This hasn't been much change yet. S squared plus omega squared, S squared minus omega squared. Now, what are the roots of this characteristic polynomial? They're what? They're plus minus omega, and they're real. What do the solutions of that equation look like then? What terms do they have in them? Huh? The roots of this are plus minus omega. So what types of solutions do you have of this equation? What does a general solution look like? Well, it looks like e to the omega t times something, which we don't know, plus something else times e to the minus omega t. What's that look like? If you plot that, what does this thing look like? I mean, you can't say exactly because I haven't said what these coefficients are. But roughly, I mean, what basically does it look like? I think it's not going to come down, except in one stupid case, if this coefficient is 0. Okay? And unless this coefficient is 0, this term is eventually going to get absolutely huge. Okay? So the point of that is that you reverse the sign on a harmonic oscillator, and you don't have a harmonic oscillator anymore. The nature of the solution changes radically. And in fact, you can easily give mechanical, simple mechanical interpretations of it. When you change the sign here, on a mass spring system, that's the same as finding yourself a negative spring. What's a negative spring? Well, a positive spring is this thing where when you pull on it, when you extend it, it pulls back. Okay? What's a negative spring? A negative spring is when you extend it, it says, oh, no problem, and it pushes you farther away, right? So there's every meter if it's a negative 1 Newton per meter spring, it's a spring where every time you extend it a meter, instead of having a restoring force, it's the opposite. It pushes you farther off, and it pushes you a Newton per meter of extension, right? So it's an anti-restoring spring. Such things exist, incidentally. They do exist. They're not passive. You can't just go to the hardware store and buy one. But for example, this happens all the time. For example, in aircraft, when you have the wrong relationship of the center of gravity to the center of thrust, and for example, when the nose pulls up, what happens now is in a conventional design of an airplane, when your nose pulls up, it's like a spring. You get a restoring torque that pushes your nose down. Okay? But for example, in an advanced fighter, when your nose pulls up, what happens is you catch more there, and in fact, it pushes you farther up. Okay? So so in fact, there you get a term just like that. Okay? You might ask, why do they do that? And the answer is you get a snappier ride, much snappier, right? Because if you don't do anything, it just flips over, right? So there better be something there to fix this, which there is, which we'll talk about later in the class. Okay, so these are your two pictures of an oscillatory system. Okay. Okay, so we've already talked about this a little bit, but we'll make it explicit. It's the idea of stability. And you take a second-order differential equation, and you say that the system is stable if all solutions of this go to 0, no matter what the initial conditions are. And then we can ask, well, when is a second-order system stable? And if we assume A is positive, you have to work out the three cases separately. And here's what happens. For real distinct roots, right, you have minus b over 2a. You have to have plus, basically plus minus this has to be less than 0. These are the two roots. The one with the plus term, since that's positive and that's positive, is the larger one. So this has to be less than 0. All right, but a is positive, so we can get rid of that. Okay, and then, in fact, it turns out that this implies b has to be positive here. Period. Has to be positive, right? Okay. Now from b squared minus 4ac less than b, you have to get 4ac is positive. So c is positive. And you don't have to follow all the details right now. The conclusion is that this is what we would call an overdamped system, or a system with real roots in the characteristic polynomial. It's stable. Extremely simple rule. If a, b, and c are positive. Okay? A, b, and c are positive. Now for real equal roots, that's easy. Both roots are b over 2a. A is positive, so you need b positive here. On the other hand, to have real equal roots, you have to have b squared equals 4ac, so c is positive. And for complex roots, the real part is both minus b over 2a, and you get the same thing. So the summary is incredibly simple. A second-order system, a second-order differential equation, this differential equation here, if all three of these coefficients are positive, I guess we're assuming really that a is positive, right? So, well, assuming a is positive, if these two coefficients are positive, then the solutions of this equation all decay with time. Okay? For example, if you have an oscillator, that's a case where one of those conditions is just slightly violated, right? Because V, instead of being positive, is 0. So it's kind of on the boundary. Surprise, surprise. When you have an oscillator, the solutions don't decay. Now, neither do they grow. And so it's kind of on the boundary as well. That's the idea. Okay? So that's stability. And what this means is, from now on, when you look at a second-order differential equation, and you see, for example, that if you have 5, 6, and 8, you can instantly say, immediately, that you don't know yet what the solution is, but in fact, it will decay with time, whatever it is, right? It could be two real exponentials decaying with time. It could have a t e to the e to the minus something t type of solution. It could be an oscillation. To actually calculate which of those it is, you'd actually have to solve a quadratic, and then you would know. Are we talking about a fast oscillation with a slow decay to 0, or are we talking about something that does 2 cycles and decays to 0, or this kind of thing, or no cycles? That's the idea. Okay. Another thing we can analyze is the decay rate. In fact, I should make a little comment about stability. Stability is inherited from a couple of fields. It is inherited from a field called automatic control that we'll look at later. It also comes from feedback amplifiers from the 30s and 40s, right? And it's widely used everywhere. So it plays a big role. And so the problem is that stability, when you say it, is marked with, it sounds like that's a good thing. And in fact, in many fields, stability is. If this differential equation, however, is an approximate differential equation that characterizes the growth of an economy, this is not a good thing. Okay? I just point this out because the terms we inherit from various fields are marked with either positive or negative connotations. Okay? So, but you should look beyond that. Okay, decay rate. So let's assume this thing is stable. All the coefficients are positive, A, B, and C. And then now we can even ask a qualitative question, which is how fast do the roots decay? How fast do the solutions decay? Again, it depends on the roots of the characteristic polynomial. So you look at those, and if the roots are real and distinct, one of these is bigger than the other. Okay? What that means is that for t large, e to the lambda 1t is much, much bigger than e to the lambda 2t. In fact, that happens very quickly. One will overtake another if the coefficient is bigger. Okay? And what that says, that asymptotically, in fact, rather quickly, depending on how far apart lambda 1 and lambda 2 are, very quickly, the decay rate is determined entirely by lambda 1. We saw an example of that already, that RC-RC circuit, where, basically, very quickly, the smaller one, the one with smaller frequency or more negative frequency, decayed rapidly, leaving you just with the second one. And it looked just like a first-order system then. And yet, lambda 1 determines it. If you have real equal roots, you have an e to the lambda t term and a t to the lambda t term. And in fact, there's a little bit of the decay rate is basically e to the lambda t. And so you could argue about this, right, about what does decay rate mean and all that. For example, some people would say, well, no, wait a minute, that's foolish. T e to the lambda t is a lot bigger than e to the lambda t, right? In fact, to be quite precise, it's t times bigger. So some people would argue but the point is that t e to the lambda t decays faster than e to any other constant lambda, which is bigger than any other lambda tilde bigger than lambda. So that's the spirit in which that works out. And for complex roots, it's given by, again, the real part. And so, in summary, it turns out that it is the real part, it's the real part of the roots of the characteristic polynomial that determine the decay rate. So in fact, let's do some, assuming you all know the quadratic formula, so I won't write down the coefficients anymore. What I'm going to do is, here's the complex plane, and I'm going to draw down the roots of the characteristic polynomial, and then you're going to tell me the nature of the solution qualitatively. So, for example, if the roots are here, and this is -3, and that's -4, what's the decay rate of the solutions of that equation? What's it determined by? No, it's this way. Remember, it's this one. It's -3, right? As you move this way, it changes the decay rate. In fact, so this is like slow decay rate. This is fast. This is fast decay. Right here, if I have a root right there, what does that correspond to? No decay rate. That's a constant. And these are growth rates. These are growth, right? So this is slow growth, and as you move out here, it's fast growth, right? So in fact, this is a picture. We're going to go over this many, many times, but this is going to be about 2 or 3 pictures that the whole class is going to be based on. This is one of them. So from now on in the complex plane, as you move left and right, and we're talking about the roots of the characteristic polynomial, as we move left and right, what it means is it means growth or decay rate from now on. Things way to the left here, very small real parts, negative real parts, those correspond to rapid decay. Things with small negative real parts, roots, that means slow decay. 0 real part, that means no decay at all. That means persistence. It's either a sinusoid or a constant. Slightly positive real part, that means a slow growth. Large real part means a rapid growth. So that's what that means. Okay. Okay, well, we can look at this, this idea of growth rate, and we can answer a question that I think was answered probably at about 100 years ago or so, something like that. And it explains why critical damping is called critical damping. Also, not to mention, for one thing, it's called critical damping because it's that value of B right between the two natures of a solution, the oscillatory solution and the exponentials. Okay, so it's critical because it's right in between. It's when the solution changes nature, type, okay, and formula for that matter. So we can ask the question: if you fix A and C, what value of B gives the maximum decay rate? These problems come up fairly often, and the solution turns out to be you choose B to be twice square root AC, which corresponds to equal roots. In other words, critical damping. Okay, so that's critical damping. And again, if it's bigger than that, it's called overdamped, and it's underdamped otherwise. Okay, and to show that this choice of B gives you critical damping requires a little bit of arithmetic and things like that, or a little bit of algebra, which actually I won't go into. Maybe what I'll do is I'll draw a picture instead, and you can read the next page on your own, which is the algebra, and instead I'll just draw a picture. Does that sound like a deal? I don't feel like doing the algebra, so it's too early in the morning to do algebra. So I'll just draw the picture. So I'm going to look at the roots of AS squared plus BS plus C. Okay? I'm going to look at the roots of that, which is given by the quadratic formula, which I won't reproduce. Okay? And what I'm going to do now is, of course, if I fix a value, A and C are positive. If I fix a value of B, I get 2 roots. Okay? So let's do the extremes here. If I pick B equals 0, what is the nature, what are the what do the zeros, almost slipped up there. What do the zeros of AS squared plus, if B is 0, AS squared plus C look like? What do we have then? Let's take A1. It doesn't really matter. So if I take B equals 0, what do the roots of this look like? What? They're pure imaginary. No, because it's AS squared plus C equals 0. It's a harmonic oscillator. Okay? So the roots are here. They're right on the imaginary axis like that. And when B equals 0, what is the nature of the solution? Are these exponential growth and decay? What is it? Is it exponent t e to the minus t? What do we have here? We have harmonic oscillator. We have pure oscillation. Okay? So what's the decay rate then? It's 0. It doesn't decay. Right? Okay. Oh, by the way, what would happen now if I took B? Oh, let me tell you what we're going to do here. I'm going to plot the roots, the two roots of this equation as we mess with B. Okay? Not exactly, but I'll get it. I'll get it qualitatively right. If I increase B a little bit now, I'm sorry, if I make B a little negative and you see AS squared plus BS plus C, and B is a little negative, where do you think the roots, where do they move to if I make B this slightly negative? Yep, they're about right there. Okay? What does that mean about the nature of the solution? Are they growing fast or slow? Slow. Okay, now you might ask, why is that? Well, this B term, as you'll see, is associated with your damping mechanism in this thing. Okay? So that would be sort of like an RLC circuit or a mass spring damper with a slightly negative, with a negative dashpot or a negative shock absorber. What that means is every time the thing oscillates, instead of extracting a little bit of energy, it adds a little bit. Okay, that was just a thought experiment. What if B is slightly positive? Where do you think the roots go? You know, we can write down the formula. We can write minus B plus minus squared B squared minus 4AC over 2A, right? Everyone knows that. But forget that for now. You can do that carefully on your own time. Just a guess. If B is slightly positive, where are the roots? Yeah, they're right here. And what does that correspond to? Oscillation, but with a slow decay, right? All right. Now let's increase B. Okay? At some point, when B, well, actually, we look at B squared minus 4AC. That's our discriminant. I'm getting those looks from SITN, which is kind of like, nah, we got a couple, we can do this. Okay. So as you increase B, that's your discriminant, right? Okay, what's the next critical value of B? When B squared is equal to 4AC, what are the roots now? They're real, and they are equal. And that's its, and I don't care, I mean, the number is when you take B equals 2 square root AC. Hey, that was our critical damping number. So when B is equal to 2 square root AC, they're real and equal. So I'm going to draw the two dots kind of right next to each other here. Okay? And in fact, the question now is, what happens as B varies between small and positive in this critical number? And I'll just draw it for you if you don't mind. It's a circle. It makes a circle or something like that. It looks like that. Okay? So that says for B in between these two, it's right here. You know, and this is no damping, and you have purely oscillatory solutions. I increase my damping, and my solutions actually tell me qualitatively what is happening as I increase the damping. What's happening to the oscillation frequency? What's happening? How do you read the oscillation frequency from this diagram? How tall it is, precisely, the height. This, right? Remember, up and down, oscillation frequency, left and right, growth decay rate. So as I increase the damping, if you walk up to a car and increase the shock and make the shock absorber have a higher parameter, what will happen to the period when you push the car down and look at the time or the frequency at which it goes through 0 again? What will happen to it? It will what? It will go down. It will decrease. Okay? What about the decay rate? What happens to the decay rate? It's also increasing. The decay rate is increasing because you're moving to the left. All right, fine. We've got to here. And now the question is, what happens to the roots now? They're both real, and I'm just going to tell you because we're out of time. But I'll tell you what happens to the roots. As I increase B further, very interesting thing happens. One of the roots moves this way, and one moves this way. Okay? And what happens to the decay rate now? As I increase the stiffness, what happens to the decay rate, and why? What happens now? One gets faster. That's great. And one gets slower. And so the overall decay rate, or what does what? It gets slower. We've just learned something, actually, which is counterintuitive. We have learned that you can walk up to a mass spring damper system. It would be easy to convince people, say, look, what I'm going to do is I'm going to take out the shock absorber, I'm going to put this one in, which actually puts more back force for a given velocity in. Then you ask people, what is going to happen to the dynamics? Is it going to get faster or slower? Is it going to decay faster or slower? And then they go, oh. Then you say, well, let me help you with some intuition. This new shock absorber is actually, for a given velocity, is going to extract more energy. And then they go, oh, thanks for the hint. When I put the new stiffer shock absorber in, it's going to decay faster. And you go, good intuition. But you're totally wrong. Okay, so this picture shows why it is that the critical damping here gives you the best decay rate. It's the farthest you can make both roots to the left. Everybody got that? Maybe I'll type this up in some notes and bring it back next time. Okay, so we'll quit here.
Professor, how do you
Yep.
know